Welcome to the lecture number 9 of the course Computational Hydraulics. We are in module number 2, numerical methods, and in this particular class we will be covering unit 5, partial differential equation with boundary value problems. What are the learning objectives for this particular unit? First objective is to discretize the derivatives of single valued multidimensional functions using finite difference approximations, and second one is to derive the algebraic form using discretized partial differential equation and boundary conditions. Let us consider a surface in 3 dimension, and with x and y this phi surface is varying. So, phi is a function of x and y only. If we discretize this using finite grid size, then with this rectangular domain for this I minus 1, I plus 1, j minus 1, j plus 1, j minus 1, we can get internal general points, and for those points we can define our partial derivatives and corresponding finite difference approximation. So, for these internal points, if we extend it to the surface, we will get corresponding function values. So, obviously, these function values are at discrete points, and intermediate points we do not have information. So, with this setup we can use the Taylor series expansion. In Taylor series expansion, for that dependent variable phi, x and y, these two are independent variables. So, with increment del x and del y in 2 directions, we can write this phi x y plus delta x into del phi by del x, delta y into del phi by del y, plus second order term for this one. We can utilize this information to get the approximation of partial derivatives. So, for that 2 dimensional domain, let us say it is starting from x naught to x m. That means we have m number of segments, and m plus 1 number of grid points or node points in x direction, n plus 1 number of node points or grid points in y direction. Again we have n number of segments in y direction. So, del x and del y, these are constant values for this particular configuration. I j is the central point for any general discretization stencil. So, with this configuration we can start discretization of partial derivatives. In this case, we have black dots are boundary nodes, red dots are corner nodes, and blue dots are interior nodes. We have seen in our ordinary differential equation discretization that we need to specify the boundary conditions at boundary nodes and governing equation for interior nodes. So, first approximation is forward difference with respect to x. So, in our discretization, we have seen for single valued with single dependent variable, if we take the forward difference, obviously this is phi I plus 1 minus phi I divided by del x. In this case, we are using the same concept and we are extending it for partial derivatives, and in case of partial derivatives we need to consider the second dependent variable independent variable, and there is no change in that independent variable because this is derivative with respect to a particular independent variable x. That is why we are increasing the index for x, and in this case we have first order accuracy like our ordinary differential equation approximation and finite difference. Similar thing is for first order backward difference with respect to x. We need to consider I minus 1 point here. Again there is no change in the index for j, but there is change in the I and I minus 1. Further, this second order center difference, for first order, this is first order derivative, this is second order accuracy. So, I plus 1 and phi I minus 1, 2 points, and this is our point I j. We can again discretize the derivatives in another direction. The first order forward difference with respect to y, again this is with del y accuracy. If we consider backward difference with respect to y, this is again with del y, and this is with del y accuracy, first order accurate, and with second order center difference we have change in the index for j plus 1 and j minus 1. This is again second order accurate method. We have two extreme points, in between we have I and j. Finite difference approximations, this is for second order center difference with respect to x. This is second order derivative, we have phi I minus 1, phi I plus 1, this is del x square. This is similar to our single variable case, and again this is del x square accuracy. Interesting point is that for this second order derivatives we need 3 points. If we consider second order center difference with respect to y, so in this case also this is change in I minus 1, I plus 1, j plus 1, j minus 1 and j. This is del y square, overall accuracy of del y square, and this is mixed difference with respect to x and y. We need to consider the extreme points. We are considering the mixed derivative at ij, mixed derivative at ij. However, we need to consider the points in diagonal direction. So, this is I plus 1, j plus 1, which is positive, then I minus 1, j minus 1, this one, and I minus 1, j plus 1, this is I plus 1, j minus 1. This two are with positive sign, this diagonally these two are with negative sign, divided by 4 delta x delta y, and this is of delta x square delta y square accuracy. So, in this case we have two independent variables and we are considering variation for both the variables. That is why we need to show this order of accuracy in terms of both the independent variables. This is a general form of differential equation with a general variable phi. We have already discussed this in our earlier lecture, and in this case phi is some general variable, lambda and epsilon, these are problem dependent parameters, and this gamma phi is a tensor. If phi naught or if phi o is the other forces, S phi is the sourcing term for this one. So, if we approximate this equation and we utilize it for defining partial differential equation as boundary value problem, then we need to neglect this term 0, this advective term as 0, this is also 0. We will consider only these two terms. In this case, del operator we are considering only variation of x and variation of y. These are unit vectors in x and y directions. So, this is del operator. So, with this information we can use a simplified governing equation to define the boundary value problem. In this case, without any cross term, we have defined this del 2 phi del x 2 So, obviously phi in previous case it is a two-dimensional tensor with gamma x, gamma y and cross terms are 0. So, if we simplify this and consider that gamma x, gamma y, these two are constants, then we can write in this format. That means gamma y and x, these are not varying with x and y. So, S phi is some sourcing term. We can define a boundary condition for a rectangular domain. So, we have rectangular domain, this is Lx for that rectangular domain, Ly for this y direction, and this is 0, 0 point. So, with this information we have defined these 4 boundary conditions. Gamma d1, that means this left boundary at x is equal to 0, and y, this is Dirichlet kind of boundary or specified boundary phi 1, and gamma 2 d, this is again Dirichlet boundary with x is equal to Lx, and for all y we have this phi 2 value, this is phi 1, and for gamma 3 this is gamma n 3, this is actually phi n. In y direction there is no variation, and top we have del phi by del y equals to 0. So, you can see that for this boundary value problem, values are either specified for all boundaries or they are written in terms of boundary conditions. So, domain discretization, this is Lx, this is y, Dirichlet boundary, Neumann boundary. Important point is for this corner points. For corner points, either we can consider it in this gamma n domain or in gamma d domain. In this case, we can consider it in gamma d domain, because in this case let us say that value is specified for these these 4 points 1, 2, 3 and 4. For this green portion, that is Neumann boundary, we can define the boundary condition based on 3 points or 2 points depending on the desired accuracy. So, let us consider the discretization of governing equation. In this case, we have discretized the governing equation with second order accurate scheme, gamma x, gamma y into this is second order accurate, minus S phi I j, which is specified value or sourcing term, we have transferred it into right hand side. So, this equation can be arranged as following. So, with this is I j minus 1 That means, if we have any general I j structure, then this is I j minus 1, this is I j plus 1, this is I minus 1 j, this is I plus 1 j. In this case, this coefficient, we are starting with I j minus 1, this is first, then I minus 1 j, this is second, I j, this is third, I plus 1 j, this is fourth, and fifth one is I j plus 1. So, we have considered the coefficients for all these points. Now, if we simplify this by using this notation, that alpha x and alpha y can be written as gamma x by delta x square and gamma y by delta y square. So, we can write this in simple form, but the problem is we cannot construct the algebraic matrix form, because we have double index notation present. In one dimension, single index is possible to form this matrix easily, but individual points will have individual governing equations or boundary condition equations. These individual points will have individual equations. So, these points are itself in ij format. So, we cannot construct the matrix directly. So, what we can do, we can introduce single index notation. Single index L can be written as I j m plus 1. This is I j, this point can be represented as L. So, L minus 1 is basically I minus j point, L plus 1 is I plus 1 j, L minus m plus 1, this is I j minus 1, and L plus m plus 1 is I j plus 1 point. We are starting from point 0 to m, that is why we have m plus 1 number of points. So, if we take the next level in y direction, so obviously there will be difference in difference of m plus 1 number of nodes. So, with this information we can construct our grid system with 0 as starting point, m here, and finally this will give the maximum number of points. We have started from this point, then we will move towards this. Again the next level will start from here, this point, again will move in this direction, again will come back to this point and move to this direction. So, we are starting with j equals to 0, j equals to 0 level. For j equals to 0 level, we have 0 to m1 number of m number of points, m plus 1 number of points starting from 0 to m. Then we will have m plus 1. Like that, we can define our nodal points with single index notation, so that we can easily form the final matrix for solution. With single index notation, the equation can be written as, in this case, we have this kind of stencil, that we have L minus 1, L plus 1. So, we have 5 points. So, L minus m minus m plus 1, L minus 1, L plus 1, L plus m plus 1, and this S phi is basically defined for I j, or S phi we can write it in terms of L. So, we can use this equation for interior points or blue points. For boundary points, we need to define the boundary condition. For Dirichlet boundary, things are clear, because we can directly specify the boundary conditions without any error. But Neumann boundary, we need to consider the second order discretization, because we have second order accurate scheme here for governing equation. So, we can include n minus 1, n minus 2 points, and this is second order accurate. With this information, we can use the single index notation to represent the thing, and we can directly use this one as equation for matrix form. Similarly, for this is for top boundary, we can use it for bottom boundary 0, 1, 2 points, and we can use the single index notation to represent the boundary condition. Again, we are getting some equation for those boundary points. Now, with this governing equation in discretized form and boundary conditions, we can form the matrix for solution. Interestingly, for interior points we will have 5 coefficients for L minus 1, L plus 1, and this is L plus m plus 1. This is for L minus m plus 1. This is valid for interior points, but if you have boundary points, then we need to consider another structure point here, which will consider the L minus 2 m plus 1, and on this side also L on this side also L plus 2 into m plus 1 to consider the 3 points. Now, we can solve this A matrix with phi defined for single index notation, and we will have something BL for right hand side. So, with this we can solve this phi L by inverting A matrix, inverting the A matrix, and this will give us the solution for the desired problem. And next lecture class we will be discussing the time derivatives in partial differential equation.